Have you ever wondered? What exactly happens inside the CPU when you type that familiar line of code? We all know that the CPU doesn't recognize English letters or understand C syntax. So how does it understand this line of code and step-by-step execute it? Today, let's start from the most basic level and unpack the entire process of how the CPU executes code. We'll uncover the mystery of how billions of transistors collaborate behind a single line of code. First, the CPU doesn't understand C, Python, or Java at all. It only understands one language, machine language, which is a series of binary instructions made of 0 and 1. Just like how we need a translator to communicate with someone who speaks another language, code must be translated before the CPU can execute it. The first stage is the compiler. Its core task is to translate high-level code, which humans can understand, into assembly language. Assembly is a human-readable version of machine language using short English abbreviations to represent operations. Each assembly instruction corresponds to one machine instruction. The second stage is the assembler. It translates assembly instructions into binary machine instructions that the CPU can directly recognize. Strings of 0 and 1. These binary instructions may seem chaotic, but they actually have a strict structure. Opcode tells the CPU what operation to perform: move data, perform addition, access memory, etc. Operands tells the CPU what the objects of the operation are, which register to use, or which memory address to access. Address mode is defined as the manner in which data is represented into the instruction format. In simple terms, the compiler acts like an English-Chinese translator, converting high-level language into assembly language. The assembler acts like a code breaker, translating assembly into the 0 and 1 that the CPU understands. This string of code is the action instruction the CPU follows to execute the code. But translation alone isn't enough. For the CPU to execute any program, it must first fetch the instructions from memory. This process relies on two key registers, the program counter and the instruction register. The PC acts like a bookmark in a book. It always points to the memory address of the instruction currently being executed. For example, when a program starts, the PC points to the address of the first instruction. The CPU uses the PC's address to send a read request to memory via the address bus. Memory responds by sending back the instruction at that address via the data bus, which is then stored in the IR. The IR serves as a temporary notepad for the CPU, holding the instruction currently being executed. More importantly, while the instruction is being sent to the IR, the PC automatically updates. In a 32-bit CPU, the PC increments by 4, pointing to the next instruction's address. In a 64-bit CPU, where instructions may be 8 bytes long, the PC increments by 8. This way, the CPU already knows where the next instruction is before the current one finishes executing, preparing for the next step. Once the CPU receives the string of 0 and 1, it must decode it, that is, figure out what this instruction is supposed to do. This task is handled by the CPU's brain center, the control unit. The control unit parses the opcode, uses internal logic circuits to determine the instruction type, and then generates a series of control signals, such as which register should be read, which arithmetic logic unit should operate, whether memory access is needed, whether the flag register should be updated. All hardware actions are triggered by these control signals. Control signals are pure electrical signals, high and low voltages corresponding to 0 and 1. They travel at nearly the speed of light, allowing the decoding process to complete within a single clock cycle. After decoding, the core execution stage begins, where the CPU's arithmetic logic unit performs the actual computation or operation. The ALU is the module inside the CPU that truly does the work. It handles all mathematical and logical operations. Its working mode is simple. It takes two inputs, data from registers or memory, performs the corresponding operation based on control signals from the control unit, and outputs the result. For example, take this addition instruction on the screen. It means add the values in register R1 and R3 and store the result in R2. The control unit sends a read signal to R1, which passes the stored value 5 to ALU's input port A via the internal bus. The control unit signals the immediate value register to pass 3 to ALU's input port B. Then, the control unit sends an addition control signal to the ALU, activating the internal adder circuit. 5 and 3 are added to get 8. The ALU sends the result 8 to the output port via the bus, waiting for the write-back stage. The ALU also updates certain status flags. 0 flag, whether the result is 0. Carry flag, whether an overflow occurred. Negative flag, whether the result is negative. These flags can affect the next instruction, such as conditional jumps. However, not all instructions are executed entirely inside the CPU. Some require accessing main memory. We all know there's a huge speed gap between the CPU and main memory. If the CPU accessed main memory directly every time, it would waste a lot of time waiting for data. To speed up access, multi-level caches are introduced, L1, L2, and L3. The logic during the memory access stage is check the cache first, then main memory. When the CPU needs to read data, it checks L1, L2, and L3 in order. Only if the data isn't found in any of them does it access main memory, saving time. Once data is read from memory, it's stored step by step in L3, L2, and L1 caches for faster future access. After execution and memory access, if needed, the final step is write back, saving the operation result or memory data, either into a register or back to memory to provide data for the next instruction. For arithmetic instructions, the ALU's result is written to the target register via the internal bus. For store instructions, data from the register is written to memory, and the corresponding cache data is updated to ensure consistency between cache and memory. Once the write-back stage is complete, the full lifecycle of one instruction ends. The complete instruction lifecycle includes fetch, to decode, to execute, to memory access, to write back. This is the classic instruction cycle. This is the entire process of how the CPU executes a single line of code. It's like a high-speed, precise symphony of electrical signals. Every clock cycle, billions of transistors switch simultaneously, working together to accomplish what we perceive as a simple line of code.